Hi everyone, I just wanted to make this quick video. So although we did skip some sections in chapter 10, the topic of determinants is on our learning objectives for this class. So I'm just going to go over determinants from chapter 10.6. There's more in that section, but I'm just pulling information from about determinants just to go over those with you guys. So for a square matrix is a matrix that has the same number of rows as columns. So it's kind of like a square, just in shapes where the length and the width are the same. So if we have 3 rows, then we would have 3 columns. So we can assign square matrices a number called a determinant, which helps us to determine if a matrix has an inverse and solve systems of linear equations. So I'm not going to go over how to find an inverse of a matrix. So in this section, we're just going to learn how to tell if a matrix even has an inverse. Okay, so the trivial determinant. So trivia just means that it's kind of like a given. So if we have a determinant A, for if A is just little a, if it's a 1-by-1 matrix basically, then our determinant of A equals A. So for the more important stuff, if we have a determinant of a 2-by-2 matrix, so say that our A is the matrix A, B, C, D. So the determinant notation is this here. So this is like our notation. Whoops. Wrong one. This is the notation. So if we have the 2 lines around the A, that is signifying the determinant. And then we could put it around our matrix here. So the determinant is AD minus BC. So you just multiply those entries and then you subtract. So for example, we're going to find the determinant A for A equals 1, -2, 5, and 6. So we do our AD minus BC. So our A, I'm going to highlight our A and D. That's 1 and 6. And then BC is -2 and 5. So it's 1 times 6 minus -2 times 5. So 1 times 6 is 6. And then here we have 2 negatives, so then they become a positive. So I have 6 plus 10 equals 16. So that's our determinant. Okay, so for the determinant of an n-by-n matrix, because this is for a 2-by-2, so for an n-by-n, so let A be an n-by-n matrix, and then remember that I is the row and J is the column. So minor Mij of the element Aij is the determinant of the matrix found by deleting the ith row and jth column of A. Alright, so we're going to go ahead and go over an example in a bit, but first I want to go over cofactor as well. So cofactor Cij of the element Aij is Cij equals -1 I plus j times the minor. So if we notice here, we have -1 to some power. So basically, this -1, if I plus j is odd, then it's going to be -1. And then it's going to be 1 if I plus j is even. Because if we had -1 to the third, that would be -1 times -1 times -1, which is -1. But if j was even, if we had -1 squared, -1 times -1 is just 1. So basically our cofactor is just the sign times the minor. So a plus or minus times the minor is the cofactor. Okay, let's go ahead and do an example. So I have A is 2, 3, -1, 0, 2, 4, -2, 5, 6. Okay, so let's find our minor. So our minor M1, 2. So the 1, remember, is the row, and the 2 is the column. So with minors, we're deleting the first row and the second column. So here, so we're deleting the ith row and jth column, right? Okay, so let's do that. So I have dashed the first row and the second column. So I canceled those out, and our minor is what's left. So that's what's highlighted yellow. So I have 0, 4, negative 2, 6. Okay, so if I find the determinant of Mij, that's going to be 0, 4, negative 2, 6. So I'm going to find the determinant. So I have 0 times 6, negative 4 times negative 2 equals 8. Okay, so my cofactor now is going to be negative 1 times 1 plus 2, or negative 1 to the 1 plus 2 power, and then m12. So I'm going to go ahead and plug this in, because that's our determinant. So 1 plus 2, that's going to be 3 to the third power, so that's going to give us negative 1. So negative 1 times 8 is negative 8. So that's our cofactor. And so our minor is the determinant of the matrix. So this is our minor matrix. But then the minor value is the determinant. And that's the one that we plug in here. Okay, let's do another example. So I have minor M33. So I still have the same matrix A. So the 3 is the row, and then this 3 is the column. So I'm going to delete the third row, that's the red dash, and then the third column. And then what I'm left with is my minor matrix. Okay, so I'm left with 2, 3, 0, 2. So I'm going to go ahead and find the determinant. So I have 2, 3, 0, 2. So I have 2 times 2 minus 3 times 0 is 4. And then I have my cofactor, A33. So I have negative 1, 3 plus 3, because I'm dealing with my minor M33. So I'm adding the I and J, 3 plus 3. And that's negative 1 to the 6th. So that's just going to be a positive 1. And then my M33 is 4. So my cofactor is 4. Okay. So all that to say is that we have the cofactor sign of the element according to the following alternating pattern. So now we've established that it follows this sort of pattern here, the one found here. So we don't have to calculate this value every time. We just follow this pattern. So we have plus here, minus here, plus, and then it's just going to alternate. So if you start with a plus up here, it's going to be a minus down here, and then it's going to alternate going down and then also across. So alternate between plus and minus. Okay, so basically this pattern is the cofactor sign of an element, which we're going to prefix to the minor. So we're going to add a plus or minus according to this pattern, and we will just add it to the minor, which is the determinant of the minor matrix. Okay, so this is going to help us find the determinant of an n by n square matrix. So if A is an n by n matrix, then the determinant of A is obtained by multiplying each element of the first row by its cofactor and adding the results. Okay, so let's go ahead and see what that is played out. So this is like a picture of it. So the determinant of A equals, so I have the first row in red because we're going to use that row to find our cofactors, basically. And so you're basically going to multiply each element of the first row by its cofactor, and then you add the results. Okay, so let's do this. It makes sense once you see it in an example, I feel like. and then I'll show you some tricks that I usually do. Okay, so we're going to evaluate the determinant of this 3x3 matrix. So the determinant of A, I'm basically going to, I have my first row, I have 2, 3, -1. I drew it in red. Okay, so our first step is I'm going to, basically I just take the first element and I put it down here. And then I'm going to find the sign of my cofactor. So if we do the alternating sign, it's going to be plus, minus, plus. So I'm going to just put a plus here because that's my sign. And then now I'm going to find the minor matrix in regards to our element 2. So for 2, I'm going to basically cancel out the row that 2 is in and the column that 2 is in. So if I cover it with my fingers, say, let's do it like this. Okay, I cover the column 2 is in and the row that's 2 is in. So that's the matrix I'm left with, 2, 4, 5, 6. Okay. And then for 3, I bring the element 3 down. And then it's a negative sign because that's the cofactor symbol from our pattern. So I have -3. And then now I'm going to cover the column and the row that 3 is in. So if I cover this column and this row, whatever's left is the minor matrix. So I have 0, 4, -2, 6. Okay, awesome. Okay, my next element is -1. So I put -1 down here. And then my sign of my cofactor is positive. So it's just going to be plus -1 times the minor matrix. So I'm going to cover the column -1 is in and the row it is in. And then I'm left with 0, 2, -2, 5. Okay. Let me leave a note. So cover row and column each red element is in to obtain minor matrix. Okay, so now we're going to find the determinant of each minor matrix. So now we're going to do AD minus BC for each. So I have 2 times 6 minus 4 times 5. That's our first one. Then for the -3 term, it's 0 times 6 minus 4 times -2. And then our third one is -1 times 0 times 5, and then 2 times -2. So for our first, I get -16 minus 24 minus 4, which is -44. So that is our determinant for our 3x3 matrix. Okay, so in this example, we expanded the determinant by the first row using the cofactors of the elements from only the first row, basically. However, we can actually expand the determinant by any row or column in the same way that we just did, by finding the cofactor and then canceling the row and column that it's in for any row or column in the same way and get the same result. So I think I have another example that shows this, so it'll make more sense. I usually just use the first row, but in some cases it's helpful to use other things, so I'll show you guys. Okay, so an important application of the determinant is the invertibility criterion. So as I mentioned, we're not going to find the inverse, but it's useful to use the determinant to see if a matrix even has an inverse. So if A is the square matrix, then A has an inverse if and only if the determinant of A is non-zero. So if the determinant of A is 0, then we would know that it doesn't have an inverse. Okay, so in this example, we're going to show that matrix A has no inverse. Okay, so we're going to actually, we'll find the determinant to see if it has an inverse first of all. But in this example, I'm going to expand the determinant by the second row so that we could perform less computations. Let me turn the row red so we know that we're working with that row. So that's 0, 0, 0, 3. And the reason why we would be performing less computations is because, look, there's 3 zeros in that row. So that means that we would be multiplying 0 times our cofactor, which would just be 0. So essentially, we would only be performing computations for the 3 in that row. Okay, so let's go ahead and do the determinant. So since we're using the second row, our signs for our cofactor are going to be negative, plus, negative, plus. So I have negative times 0, and then I'm just going to write cofactor 2, 1, plus 0 times cofactor 2, 2, minus 0, cofactor 2, 3, plus 3, oh, that's supposed to be a C. Alright, plus 3, cofactor 2, 4. So basically, I don't have to find any of these because they're 0, so they cancel. So I just only have to find 3 times cofactor 2, 4. So let's go ahead and do that. So I go ahead and I can, I can cancel the column that 3 is in and the row. So I get 1, 2, 0, 5, 6, 2, and 2, 4, 0. Okay, so now I have 3 times this new 3 by 3 matrix. But in order to use our AD minus BC, we need to have a 2 by 2 matrix. So I'm basically going to expand this matrix again. And then this time, I'm actually going to expand by column 3. And that's because I have 2 zeros in that column, which would make doing the determinant easier. So I'm going to go ahead and expand by column 3. So I have basically my first element 0. We know that cofactor cancels. And then my third element is 0, so that cofactor cancels. So I'm really going to be only using the negative or the 2 element. And then let's go ahead and look at our pattern. So our pattern was plus, negative, plus here. So I'm going to go ahead and use that pattern. So it's plus, negative, plus. So that's our cofactor sign. So it's going to be negative 2 because I'm using the element 2. And then let's go ahead and I'm going to cancel the row that 2 is in and cancel the column that 2 is in. So I'm left with 1, 2, 2, 4. So I do 3, negative 2, and now I could find the determinant since it's a 2 by 2. So I have 3 times negative 2, 1 times 4, minus 2 times 2. That's going to be 0, actually, when you multiply all that out. So our determinant of A is 0. Therefore, we can conclude that A does not have an inverse. Okay, so even though you could use basically any row and column that you'd wanted to find the determinant, our work is reduced considerably when we have zeros because we don't have to evaluate those cofactors of elements that are 0. And so in that way, sometimes we have matrices and we could actually add multiples of rows together or multiples of columns together within a matrix to get new rows and columns with zeros to make our work easier. So that's similar to like when we were doing linear systems of equations, when we'd multiply multiples and add them, and then also when we were doing like our row reduced echelon form or echelon form, basically, when we're adding multiples of rows together to get columns or rows with zeros. So we could do that to make our matrix easier, to make our determinant easier, or you could just go ahead and go for it and find the determinant. So whatever works for you guys, but okay, so that's the quick rundown on determinants. I hope that was helpful, and I'll see you guys next time.